Check, check. I've got my levels. Here we are. And we are good. So, all right. So today we're talking about common logarithms. All right. So we briefly mentioned this yesterday, that log base 10 of anything can be written as just log of that thing. All right. So it is implied, if no base is written, that the base is 10. Okay, so that is what's referred to as a common logarithm. And we're going to use some properties of logarithms and talk about how you can discover other values of logs, and this is kind of how they generated some of these tables in the past. So let's say given, let's say log of 2 is 0.301 and log of 3 is 0.477. Yep. We're going to find the following. So let's figure out what is log of 4 going to be. So we'll do that one together first. So if that was the only information I know, how could I find out what log base 10 of 4 is, or what just log of 4 is? Ideas?
You need a calculator?
Well, if I didn't have a calculator, what if I knew these only through some sort of estimation technique that, like Ellen was describing the other day, making a table and just trying more and more values, calculating it out exact. And we've realized that we were accurate to 3 decimal places for this. What would a quick way of figuring out log of 4 be?
Could you just subtract log 2 from log 3 and then add that to log 3?
Because it would go up.
Or you could,
Well, it's log 10, 4.
or you could do 2 log of 2.
Okay, so I think
10 to the x equals 4.
so. This is the same as log of 2 squared, which Zeb described as 2 times log of 2, right?
Yep.
And since I know what log of 2 is, that's 0.301, then I know what log of 4 is. I just have to double that, so 0.602.
Would finding like 10 to the x equals 4 work if you had like...
Right, and that's essentially what we have solved here, but we still don't know what that x would be, but here we were able to use a previously known fact to figure it out. So that's kind of how you can start expanding the facts that you know based off of some different values you've got. What if I want to figure out what log of 6 is?
Log of 2 times log of 3.
So that's log of 2 times 3. So what, do I just multiply these?
Now you add them.
You add them. Isn't that crazy? Right? Because log of 2 times 3, the log of a product, is the sum of 2 logs, so that's log of 2 plus log of 3. Right? So that would be 0.301 plus 0.477, and I would get 0.778 would be log of 6. All right? So using those facts, I'm able to kind of expand on these concepts. What if I wanted to know what log of a quarter was? Now, let's do an eighth. So 10 to what power is an eighth is what we're asking. So we're expecting that. Well, it's kind of a bizarre thought. 10 to a power being something less than 10 will have to be, that power will have to be less than 1. But using our previously known facts, is there a way I could write 1/8 in terms?
Log of 2 to the negative 3rd.
log of 2 to the negative third, right? 2 to the negative third is 1/8. And then using our power property, I can move that negative 3 out front. So negative 3 times log of 2. So that is negative 3 times 0.301, or negative 9.0. Nope. Negative 0.903. Silly me. Right, so it's not terribly bad to be able to figure these things out, right? How about, what if I wanted to know log of, let's do 18. Let's have you guys figure out what that would be. Try to figure out how you'd set that up. What?
There's lots of different ways of deciding.
Now, what would you suggest? Does anyone have an idea? Based off of still the information that we have. Yeah, we could do log of 6 times 3, since we just did discover log 6. I could also break 18 down into 2 times 3 squared. Right? That's the prime factorization, which is the same as log of 6 times 3. I could have done log of 2 times 9, but I didn't find 9 yet, but we would be able to. We'd be able to do all that. But I'm going to do this version. So log of 2 times 3 squared, that's the same as log of 2 plus log of 3 squared. So that's the same as log of 2 plus 2 times log of 3, if I use the power property, right? So this is going to equal what? 0.301 plus 2 times 0.477, was it?
Yeah. So 301 plus 0.954.
Sure. And what we're saying, 1.255. I agree. So 10 to the 1.255 theoretically then is 10, or is going to equal 18 exactly. All right. And just to verify some of this with our calculators, which we theoretically didn't have a moment ago. Whoa. Let's see if I can get some focus on this. And we're good. All right. So let's see. So is 10 to the, what was the decimal we just said? 1.255. Theoretically, we're expecting this to be 18, and that's pretty darn close for a 3 decimal approximation, right? Actually, that's even worse than just a 3 decimal approximation. That was 2 3 decimal approximations, right, that were then used in kind of some evaluations. So it got even a little bit further off than that. And just to verify, if I said log of 18 and just hit enter, all right, there's that 1.255 and a little bit further out than that. Now I could actually just do 10 to that and see if it, oh, what did I just do? Oh, I hit second entry again. I've been doing that forever now. Second answer, right? And notice calculator's like, yeah, that's 18. Right, so yeah, that's kind of an interesting way that you can build more facts about logarithms using some previously known logarithms. Now what I've got here is, now I've actually given this to you guys before a long time ago. I'm going to pass these out, but I just reprinted them. I believe most of your calculators will probably have some sort of log button on it. But if not, you could use some of these decimal approximations of logs to be able to analyze that a little bit further. And so basically I've got some logs of different numbers estimated here. And kind of the scale isn't consistent, so it does end up jumping around here, especially at the end. But yeah, so the idea is that we could use this. And so notice here's our estimate of log of 2 is 0.301. Right? Log of 3 is the 0.477 that we had. We just found log of 6 earlier was 0.778. Let's see, log of 18. There's the 1.255 that we had. So I made this in Excel, so that's how I get these pretty good estimates. But I just want to look at some general analysis of this. So notice that log of 0 is undefined. Could someone explain why that would be the case?
Can you not have
You
log
can't
of
have,
nothing?
you can't have a power of 0.
Yeah.
Well, you can't have a power that will equal 0.
Right. So 10 to what power is 0?
There isn't.
There isn't one. Because 10 to the 0
One.
is 1.
You could get infinitely close to 0.
You can
Right,
never
but we'd
actually-
never actually get there.
Asymptotic.
And then notice log of 1. 10 to what power is 1? So that's 0, right? So I have to kind of like think backwards here in order for this to work. Right? 10 to what power is 2? 10 to the 0.3, right?
301.
Skipping down, 10 to what power is 10? So that's 1, that makes sense, right? And notice that for values less than that, right, we have decimals. For values greater than that, we have numbers that are, well, still decimals,
What does
but bigger than 1.
ln mean?
That one we might save for tomorrow.
That was like the whole like log of E thing, right?
Yep, log base E. But so yeah, so then I've got values of log all the way down to I think 30, counting by ones anyway, and then I've got then I count by tens, and then I start multiplying by factors of 10. So notice log of 100 is 2 because 10 squared is 100. Log of 1,000 is 3 because 10 cubed is 1,000. Right? And then I've even got, some other values there that you can spot. Actually, so I can actually use this table in kind of the same way that I just did a moment ago. What if I wanted to figure out what... let's figure out one that wouldn't be on this table. Let's figure out what log of 120 is. Now I could actually do some little tricks with this. So that's log of 12 times 10.
Log of 5 times, or log of 6 times 1.
Yep. Yeah, we could combine it with that. So that's log of 12 plus log of 10.
Log of 12 is 2 squared times.
Log of 12 from our table. Let's see.
1.079.
Let's see if I looked it up. Right there. Would give me 1.079. And log of 10 is 1. So then I would add those together and get 2.079. Right? What if I wanted to figure out what log of... let's do 2 more. What about log of 3,000?
Log of 3 times
and we'll do log of 0.0007. So the top one is log of 3 times 1,000. So that's just log 3 plus log of 1,000, right? Which I could think of as 10 to the third. Is it not working with pencil sharpener?
No, it is not working.
Huh. So unfortunate. Log of 1,000 is 3. I could actually have said that's 10 to the third. Right? I do happen to have log of 1,000 on this, but if I didn't know it, right, log of 10 to the third, and then power property, I could pull the 3 out front. So that's just 3. And log of 3 is, oh, we actually had that already. That's the 0.477. Right? So I end up with 3.477. Now, in terms of vocabulary, it's kind of abstract, but this whole number is referred to as your characteristic. And this number is referred to as the Mantissa. Let's see, make sure I spell that right, double S. All right, so just some weird vocab for basically for numbers that I can break apart. The Mantissa is always going to be a value between 0 and 1. I'll just call that like that. And then your characteristic will be an integer.
So what about like 1/3, 2.5? That's not a whole number, but it's greater than
Well, it would end up being, the characteristic and Mantissa would be somewhere in between that. Or wait, you're saying if I wanted to find the log of 2.5?
no, like
What would it be called?
the vocab thing, what would it be called in like 2.5? Because it's not a whole number, and it's greater than 1.
Well, if I was to get to that point, like, for instance, wait, what do you mean greater than 1? What did you just say?
Because the Mantissa is a decimal that's less than 1. So calculate.
So your characteristic in that case would likely have been 2, and then your Mantissa would have been the 0.5. It's
Hang on,
like
can the characteristic have decimals?
No. So this is
So it would have been like a 2 and 1?
a 2 and a 1.
Yeah, like if I had if I had log of 27, that's like 1.43. That's greater than 1, but it's not a whole number. So what would we call it?
Well, the characteristic of 27, if it was 1.43, the characteristic is the 1, and the Mantissa is the 0.43. So the Mantissa, in this case, so far, it appears as though the Mantissa will just be our decimal part. However, in our next example, it will be a little bit trickier for when you take the log of a number that's a decimal, I guess. Does anyone have an idea of how we could set up this one here? This is log of 7 times something.
0.0001.
True. I'll write it out like that for starters, 0.0001. And do you know how, so that's going to be log of 7 plus log of that.
Log of 10 to the -4.
That's 10 to the -4th.
Or 10 to the 1/4.
No, that would be a cubed, or 4th root of 10, which is different than that. Okay, so the characteristic, more accurately defined, let's see if I've got a description for it, is going to be the value of log to some power of 10. Okay, whether that power might be negative or positive. So in this case, what do I get for log of 7?
Wait, so the characteristic can only apply to
Log of 7.
log
Log,
base 10.
logs of 10, yeah.
0.845.
0.845 is what we get. Plus, and then what's this going to equal? Well,
-4.
1 times -4, which is -4, right? So my characteristic in this case is the -4, and the Mantissa's
5, negative 3.
is that. And that's what I wanted to point out here, is that the Mantissa is not equal to the decimal from our answer in this case. So what do we end up getting? -3.155 when I combine those.
Yeah, I just wrote it as 0.845 minus 4.
0.8 for what?
For the second to last step.
You wrote it as 0.845 minus 4? Yes, okay, yep. Yeah, that would be fine as well. So your characteristic, in this case I want to point out, the characteristic was not -3, and the Mantissa was not 0.155. And that will only be true when your answer is negative, that you have to worry about this weird little switcheroo. Basically the characteristic is going to be like the next smallest negative whole number, right? So -4, and then the Mantissa's just whatever 1 minus that decimal change is, ends up being how it works out. But that's just some kind of like arbitrary vocabulary. We don't end up using it that often. Well, yeah, let's see. Oh, so what I want to point out is that means that 10 to this power should equal 0.0007, right? So let's actually verify that. So 10, where am I here? So is 10 to the negative 0.3155, was that our decimal, I think? No, what did I do wrong? Oh, that's what it was. Thank you, guys. 10 to the negative 3.155. Huh. And is this the right answer?
Yeah.
Close enough.
It is, but notice that the e to the negative 4, that is scientific notation, right? So that is 0.0006998, and that 699 would round to the 7 that we were talking about. So I just want to point that out there. All right, so that's some kind of like using logs as building blocks to find other logs, and then just that little bit of vocabulary that's a little bit weird. But yeah, so now we have our table that we can do wonderful stuff with, calculate all sorts of different things. And then also you can clearly use your calculator, right? So I could have just hit log of 0.0007, enter, and I would have gotten that answer right off the bat, right? So your calculator communicates in only 2 log languages, which is log base 10 and ln, which is log base e. And looking at our table, even though I'm not talking about this technically until tomorrow, let's see, get some focus here. There we go. And good. I just want to point out that ln of e is the 1.00. So right, so log base e of e to what power is e?
1.
Is 1. So that's what that is. And I've got e somewhere in between 2 and 3 there.
Why is the 1 really bold?
Just because I wanted to point out that kind of like my pattern skipped and that thing switcherooed there. And I think E is what, 2.718281828 is the approximation for E. But we'll talk more in detail about that later. So these are the only 2 languages that our calculator speaks. So eventually we'll have to get to a problem of how do I solve, right, log base 2 of something, because our calculator doesn't speak that language, and we mentioned that yesterday. Let's see, I think we did. We're okay on those. And that's why we have this change of base formula, which I think I can grab a snapshot of here. Can I get a snapshot? So the change of base formula is going to allow us to solve for logarithms that aren't in that form.
Could you?
Yep.
So,
Yeah, I'll leave that up there for a minute. And I just want to point out that there's a lot of restrictions on all of these variables once again. Let's see, so if a, b, and n are positive numbers, and neither a nor b is 1, then the following equation is true. So, let's evaluate what is log base 2 of 3. So according to this, all I have to do is do log of 3 divided by log of 2. And in this case, because we're most familiar with log base 10, that's why I'm using my value for b is just 10, right? So I'm changing from base 2 to base 10, right? And that's how I do it. Technically, this would also equal ln of 3 over ln of 2, because I can work in base e as well. Or I could do log base pi of 3 over log base pi of 2, and it wouldn't matter. Although that wouldn't be very useful because we don't
Base pi.
calculate stuff that's not in base, 10 or e. So what was log base 10 of 3 from earlier? 0.477.
Yep.
Over log of 2,
Log.
0.301. And notice I've got a fraction that I would expect is going to give me something, it's going to give me something bigger than 1, which does make sense because 2 to the first power would have been 2, so 2 to something bigger than 1 would give me something bigger than 2, right? So let's actually calculate what that is. Let's see. So the way I'd plug this in a calculator is I just do log of 3, close parentheses, divided by log of 2. I think technically I can get away without closing these parentheses, but so 1.5849. 1.585, we'll call it. Okay? And with this, if I wanted to verify this, I can do raise 10 to that power. And what should this... No, wait, my bad. 2 to that power. Silly me. Oh, what did I do? Let's see. I'm all over the place. 2 to the second answer. There we go. And notice I do in fact get 3.
Under 3 is 3 to that.
Not anything helpful for the question that we were asking. Now, so we can now calculate those, all day. And that will be helpful for solving equations like the one I accidentally put on your quiz yesterday, where we had, what was it, like 4 to the x equals 9?
Yeah.
Today we'll know how to solve that and get an exact answer for that using this change of base trick. Because the problem with that was that 4 and 9 could not both be written in terms of the same base, right? Let's see, one more thing I think I've got to tell us before we move on is antilog.
Is that the inverse of log?
Yeah. So if I wanted to calculate the antilog of, let's say, 3, that is kind of the opposite of a logarithm. And all this means is, well, let's see. The antilog is the inverse of a log, all right?
Mm-hmm.
What was the log the inverse of?
Squaring.
Not quite squaring.
Exponents.
Exponents, right? So if this is the inverse of a log, which is the inverse of like an exponential function,
This is. Exponent.
this is an exponential function. All this means is, because this is log, this just means 10 to the third. All right? It's kind of like that quote, like, the enemy of my enemy is my friend.
It's just
You know, the inverse of an inverse is itself. Right? So it's just flip-flopped back to itself. So if you ever see that, that's all that's referring to. And then there's also technically anti-ln of a number would just be e to whatever that number is. And even in terms of the calculator's placement of the log buttons, so the log button is there, and its inverse, antilog, is right above it. Right, so 10 to the x. So if I want the antilog, I would just hit second antilog 3. Let's see what it, and it just is 10 to the 3. All right, so it's just kind of like a language piece, but we usually wouldn't think of things in terms of antilogs. It just looks cool, I think. All right, so let's get into solving. Let's put this to use. Finally. All right. Here we go. Where am I? Example. So let's solve that problem that was wrongly on the quiz the other day. What if I want to solve 4 to the x equals 9?
log base 4 of 9 equals x.
Well, now we had the ability to remove logs from both sides of an equation, right? If two logs of the same base are equal to each other, then their ofs were the same. So what I'm going to do is actually add logs to this equation. So I'm going to write this as log of 4 to the x equals log of 9. Because you guys already knew that we could go backwards, right? If I have two logs of the same base, then their insides are equal. So technically we can add logs to things as well, all right? To both sides, all right? It has to be to both sides exactly. You can't just like add it to portions of an equation. And I chose to work in log base 10 because that's what we're familiar with. So now how could I solve for x? What could I do here?
X times log 4 equals log 9.
Right, this is why logarithms are so powerful, is I can solve for variables within exponents. Because of the power property of logarithms, I can move this x out front, and I would have x times log of 4 equals log of 9.
Log 4 equals log 9.
So now how could I solve for x?
Divide both sides by x.
No.
By log 4.
Right, log 4 is just some number, so that's essentially our coefficient. So if I divide both sides by log 4, I would get x equals log 9 over log 4. I could also think of it using change of base. I could have thought of that as log base 4 of 9. Which, I mean, in reality, that's what I wanted to know, right?
That's what you wrote, log base 9. Log of 9. Log of 4 is just a way of writing log base.
Yeah, this is, logarithmic form of that equation, right? That's equal to x. But now I actually know how to do it, where this is just going to be log 9 over log 4. So log 9, close parentheses, divided by log of 4, enter, and I get 1.585. Did we have that answer show up earlier?
Yeah.
When I had 3... That's
Log of 3 over log of 2.
Yeah, it reduces to the same thing because that's funny.
It's
Because both of those were squared, so both of those, the numerator and denominator would have been doubled. That is funny. I didn't plan on that. 1.585.
I guess they have the same base ratio.
So this would be valuable to us, this ability of solving, if I was asking a question, right? We talked about at the beginning of this chapter exponential growth and compound interest, and I could have back then said, if I put $1,000 in a bank account for 10 years at this interest rate, how much do I have after 10 years? And you could have told me that. But if I asked a question in a slightly different way, all right, let's say I put $1,000 into an account. I want to have $1 million, all right? And let's say our interest rate, N, compounded annually. Let's say it was 5%, all right, which is 0.05. And now I'm asking the question, how many years will it take until I get $1 million? All right, which is a valuable question that we wouldn't have been able to answer without this logarithmic power. So the formula we're using is A equals P times 1 plus, actually that's my R, isn't it? Darn it, I mislabeled N. We'll watch this, I'll just scribble out part of it. That's an R, pretend. 1 plus R all to the T is what I did, yeah.
T for time.
T for time, yeah. So I want to figure out how long does it take to get my $1 million. All right, so let's plug in what we got. So 1 million plugged in for A is equal to 1,000 times 1.05 to the T. Yep. Anyone have any estimates for how many years it'll take?
Less than you'd think.
Maybe less than you'd think, but
Because of compounded interest.
right. But also, it's probably going to be more than one generation of a person's life. We'll see. So how could I solve this? Any ideas?
Add in logs.
We could. I'm going to simplify it a little bit first. You wouldn't be wrong for adding in logs just right then, but I'm going to do this.
So it's 1,000.
Yeah.
1.05 to the T.
1.05 to the T. Now I can log it. So log of 1,000 equals log of 1.05 to the T, which is T times log. T time. That's right. Log 1.05. Log of 1,000 is technically 3. You could leave that as log of 1,000 until the end if you wanted.
So no, that'd be 3 over log 1.05.
And then divide both sides by the log of 1.05. Right.
Hang on,
T log. And I get T is, and I'll just do this on my calculator, so 3 divided by log of 1.05, and I get 141.58 years.
So 142 years.
Yeah, 142 years. Right, so I'm able to answer a question like that, whereas without logarithms, we wouldn't have been able to solve that. All right. So let's do, I think I've got one more crazy.
141.58.
Say what?
141.58.
Yeah, 141.58. Right, and so any exponential growth or decay question where my unknown is the time, right? So for instance, if someone was trying to carbon date something, and they wanted to figure out how long ago was this, or how many years until it only has half of it, carbon-14 remaining in it, right? You could use logarithms to answer that sort of question. And then here, of course, just somewhat of a more arbitrary type of question. What if I wanted to solve 5 to the x minus 1 equals 2 to the x?
I'm gonna want to add logs.
Yep, so we're going to log both sides. So log of 5 to the x minus 1 equals log of 2 to the x.
Multiply.
Right? Power property, so I can pull those exponents out front of each log respectively. So I'll have x minus 1 in parentheses times log of 5 equals x times log 2.
X log 2.
Yep. Now any ideas?
Get all the variables on one side.
Yeah. But in order to do that, I'm going to have to first distribute over here. So I'll distribute the log 5 to both of these. Right?
Add log 5 to both sides.
Yeah, we'll add log 5 to both sides and subtract x log 2 from both sides, because our goal is to get all of the variables together and all of the non-variables together. So that would look like x log 5 minus x log 2.
Hang on.
Equals log 5.
Right? So the way we did that was we brought that over here and this over there, right?
Hang on, can you give me a second?
Yep. Now anyone have any ideas? How am I going to get x by itself?
Just find the logs.
Combine the x log 5 x log
Multiply.
Hang on.
You could actually
X
rewrite.
log 5 halves. Equals x log 5. Or equals log 5.
Yep, that would work. I could use the difference of logs to write the log of a quotient. The first thing I'm going to do is actually factor out an x, which is technically taking place before that description as well. So this is x times log 5 minus log 2 equals log 5.
Hang on.
Yep. And we're almost done.
Then be x times log 5 halves.
Right, so that's log 5 halves, or I can just leave it the way it is. To get x by itself, it's being multiplied by this big thing, which this is just some number. So I can just divide both sides by the big ugly log 5 minus log 2.
Hang on.
And
My
I
pencil
get-
is quite dull and pencil sharpener is not
And when I plug this in a calculator, I'll have to be a little bit careful here with my numerators and denominators. So log of 5 divided by, and I'll have to open parentheses around this bottom here, right? To make sure that all stays in the numerator. Log 5, close parentheses, minus log 2, double close parentheses. All right, because this will have its own, this will have its own, and that'll have its own. So yeah, so plugging it in a calculator is a little bit tricky. But I end up hitting enter, and I get 1.756. And if we wanted, I could even do a check in the original problem to verify this if we'd wanted to. But yeah, so with all of our abilities in manipulating logarithms using their properties, we can actually now solve pretty much any equation with variables in exponents, which is quite nice. Quite
I
nice.
sure hope there's nothing left because I'm all out of room.
Yeah, I think we're done.